Here we go, Bayes' theorem. Bayes' theorem, I am a huge fan of well, first of all, you need to know when to use Bayes' theorem, recognizing the proper scenario. So that's number one. The other thing that I am a huge fan of is the tree representation for understanding Bayes' theorem, not memorizing a crazy formula. It just never goes well when you have to memorize it, but when you have the tree representation, all is fine. So here's what Bayes' theorem says. All right, we are going to make a tree and we're going to say that there's two possible outcomes for now. We can change that later, where either A can happen or maybe A doesn't happen. And we'll assign probabilities to that. Maybe we'll call it like 20%, and therefore, because there's only two options, then therefore this has to be the other 80%. Now, given A has occurred, we can now have the probability of B given A has happened, or the probability of not B given A has happened. Because if you're standing at this spot on the tree, you're already at A. So therefore, you know A has to happen. And again, now we're going to have two separate sets of probabilities, maybe a 30% and a 70%. Yes, I'm making these up. These could be anything. I'm just doing examples. All right. Now we could have another set from the tree here where again B can happen or B might not happen, but in these set of branches we know it is given that A did not occur. So you can see Bayes' theorem uses the conditional probabilities from before, and we're going to look at each branch. Let me make up something silly here, 40 and 60. There we go. Okay, and we're going to look at the branches kind of individually. Now, the traditional conditional probability, like so, for example, that we did in the last section, where if I did like for example, what's the probability of A and B occurring? Well, do you see we'd be looking just down a branch? We'd be saying, okay, probability of A would be me going down this branch. Then the probability of B happening would be finishing off going down this branch. And so therefore, the probability of A and B is the probability of A times the probability of B given A. And you can see that straight from our tree. So that'd be 0.2 times 0.3, just with the numbers I made up. Right, so makes sense? So you can use this, for the problems we were doing in the last section as well. But here's the fun question. Here's what Bayes asks. They say, what is the probability of A given B? Now notice, or any variant of that, but notice here's the key thing that I'm pointing out, is in our tree, it's switched. Normally we have B given A. Now they're asking it backwards. They're saying, what is the likelihood of one of our in-between values? So I call these the branch, and I call the ends the leaves, right? So instead of asking about a leaf, saying what's the likelihood of getting to this end, it's saying what's the likelihood that if you know B happened, what's the likelihood of you passing through A? What's the likelihood of you just going down this path? And what makes Bayes' theorem really, really cool is it's just regular probabilities. There's nothing new to learn here if you kind of think about the tree. So it is given that B has occurred, right? The way that I asked this question, we know B has happened. So therefore, every branch that has a B, we're going to keep. Anything that has a B prime, we don't care about because we know B happened. It's not B prime, it's B. So therefore, these two branches with these two leaves, we're going to keep these branches. These are possible. Okay. So, and I'm going to highlight them just to kind of give an example here. So, therefore, possible branches would be this one going through A up to B not A, or B given A, excuse me, or going through not A and then going to B given not A, because our condition is B has to happen. And the question is how likely is it that A happened too? So, here's how we do our probabilities. What is the probability of the branch like we did before, 0.2 times 0.3 for the top branch and 0.8 times 0.4 for the bottom branch? Well, that would be our total outcomes, right? I could have potentially 0.2 times 0.3, or I could have 0.8 times 0.4. Those are your total possible outcomes. And those are going to be adding because it's one or the other. It's leather or cloth, if you remember back from the Ford Explorer question. or Ford Escape, whatever Ford it was. But anyway, it's the one or the other, so they don't both happen simultaneously, so therefore it's addition. So that would be my total possibilities. That would be my total number of outcomes, right? And those are because those are all my branches. Now the question is which one's the desired? Which is the one that we're looking for? Well, the question asked for A. So which branch passes through A? Well, that's my numerator, so it's 0.2 times 0.3. And yes, you will notice they match, right? There's both that option is both in my numerator and my denominator, and that's okay because remember, your denominator is your total number of outcomes, your numerator is your desired. So that's Bayes' theorem. There's no formulas to memorize. There's nothing crazy going on here. So walk through the process one more time. What do? You look for the given. You look for the what do we know. You find the branches that have that. You star them. And if you wanted to, you could even scratch out the other ones. You say, you are dead to me, branch. I don't need you. All right, now, I say that's my total possible outcomes anymore because I know B happened. So therefore, now I highlight my branches and I say those are my total outcomes. And then I say, all right, which one is the question? Which one are we asking about? We're asking about going through A. So that's my numerator branch. Okay, so let's do one with context. Okay, when getting email from work, there's a spam blocker turned on. We have Gmail, and so there's a spam blocker. 1 out of 20 emails are marked as spam. Of those marked as spam, 1 out of 5 are incorrectly marked, so meaning they weren't spam, but they got marked as spam. In my emails that actually get to my inbox, only 1 out of 100 are spam that should have gotten marked. So 1 out of 100 will get through. So I'll have 99 good ones and 1 bad one, if that makes sense. What is the probability that an email that is spam will get marked as such? Oh my goodness. Okay, how do I translate this words into that picture up above? Well, here's the deal. Here's what you're looking for. Notice your in-between branch, your A, the part of the branch, is not a conditional probability. So when you're looking through the problem, what you're going to do is look for something that isn't conditional. Just it's the probability of eating breakfast. There's no probability of eating breakfast given that. No, none of that stuff. Just what's the probability? Well, I know it's this. So let's read through this again and look for something that isn't a conditional probability. When getting email from work, there's a spam blocker turned on. 1 out of 20 emails is marked as spam. Oh, there we go. 1 out of 20 emails is marked as spam. So what is that saying here? It's either going to go to my junk box or my inbox, right? So we'll kind of say it's either going to junk or going to in. Okay. And this is saying 1 out of 20 get sent to my junk. So 1 out of 20 goes here, 19 out of 20 goes there. Perfect. Now, next. And of those marked as spam, so the ones that go to my junk box, 1 out of 5 are incorrect. So what are we saying here? How do we want to label this so it doesn't get confusing? I will caution you not to use the concept of correct or incorrect. So why don't we just use spam, whether it's spam or it's not spam? How about like that? Okay. Because correct and incorrect it takes on different meanings depending on what box it's in, and that gets very confusing. So we'll just go with this way. We'll go with this. So what I'm going to do is say, all right, so therefore spam and not spam. So now you'll notice here, I will have spam in my junk box or not spam in my junk box. Or I'll have spam in my inbox or not spam in my inbox. And using that definition makes it much easier to keep straight. Okay, so now let's go back here and read now. And so for those that got marked as spam, which means they go to my junk box, 1 out of 5 are incorrectly marked. So what does that mean to be incorrectly marked? It's not spam, but it's in my junk. So 1 out of 5 are wrong, 4 out of 5 are correct. Okay. And then in my emails, so in my inbox, only 1 out of 100 are actually spam. Okay. So 1 out of 100 is spam, which means 99 out of 100 are not spam. So now let's listen to the question. What's the probability that an email that is spam gets marked as such? So we know it's spam. We know that. So then the question is what is the likelihood it gets marked? What is the likelihood it gets sent to my junk box? So this problem is saying what is the probability it gets sent to my junk box given that we know it is spam? And so now you'll see the question is right here. What's the likelihood it goes through that path? It's going to the junk box. So therefore, and we know though, the ones we're going to keep are the ones that go through spam, right? So therefore, I'm going to star my spam rows, but actually, you know what I'm going to do? I'm going to take away that highlighter for a second. There we go. Okay, so I'm going to star my spam rows, doot, and doot. Now, those are going to be the two rows that I keep. So therefore, the probabilities to get to each of those stars is what's going to go in my denominator. So it's 1/20th times 4/5 plus 19/20 times 1/100th. My numerator will be, because that's all the stars, I have two of them, so they both go in my denominator. And my numerator will be the one that goes through the one I want. It goes through the junk box, right? So that'll be 1/20 times 4/5. And you'll notice this happens to be the same pattern as the one I did up above. It happens to use both the top and the third leaf, but that's okay. So here's another problem. All right, let's try this one. What is the probability that an email that is spam will not get marked? So how does that change the problem? Well, notice probability. All right. So what is the question? Focus on the question. The question is what is the likelihood that it will not get marked? We don't know, right? So therefore the question is what is the likelihood it's going to end up in my inbox given we know that it is spam. So therefore given that it's spam. So notice it's the exact same branches. It's the exact same. I'm going to use still the same starred rows because we still know it's spam. But now the question isn't what's the likelihood of it going to my junk box. The question is what's the likelihood of it going to my inbox? And so here we go. So it would be the exact same denominator because it's the exact same leaves. We know it is spam. So now the question is what's the likelihood that it gets the inbox? So the numerator now becomes 19/20 times 1/100. And there you go. So you might be saying, who cares? Like this question's weird. How do you know an email is spam, and why do you care what the likelihood is of it going to your inbox is? Well, the person who's sending the spam. This is what they care about. So a lot of this math is now used on the business side of things. This is not from the consumer side where you're just saying get rid of this annoying email. This is the other way. This is the business saying I'm sending out spam. What's the likelihood someone's going to see it? Or the person creating the software, this is how they test their software. They send spam at it and they figure out these things. So that is our first Bayes theorem problem. I have a couple more I'm going to do with you, but I'm going to do them in the next video. So if you aren't feeling confident yet, don't worry. We've got a few more to go. All right, we'll see you then.